Okay. So, we still stick to vertex covered. Is there anyone who needs now definition of vertex cover, or are we done with after 3 lecture? We can assume that we know the definition of vertex cover. Okay. If you need a definition of vertex cover, I can repeat it, but like I hope maybe you have put it as a sticker in your room. Okay. Okay. So what did I prove last time? So the lemma which we showed last time is that following. Let G be a graph, okay, and K be an integer. K, yeah, be an integer. Okay, and I say let's suppose you have V1, V2, and ordering, so the degree of V1 is equal to degree of V2, degree of V. Okay, so these vertices. So this is in the sequence in the decreasing order of degree. Then what did we show? We showed that this is the lemma. We said if G comma K is a yes instance, meaning it has a vertex cover of size at most K, then there exists a set S, or there exists a vertex cover S of size at most K such that S intersection V1, V2, Vk plus 1 is not equal to Nk, and from now onwards I am going to denote in this sequence. So, when I write Sk plus 1 or S whatever it is, it will mean the first that many number of vertices. Okay. So, this is just a definition. Okay. This we proved last time and I am not going to reprove this. Okay. But now using this can be designed an algorithm. Okay. So, my question is, could we use say lemma x, could we use lemma x to get design an FPT algorithm vertex cover. Okay, guys. Okay. Right. So, this is what we proved last time, right, that basically what I am saying, there exists an optimum solution that you are guaranteed that contains at least one of the top K plus 1 vertices. Like in plain word, this is what it means, right. Can we use that to design an algorithm, right? Could this lemma be useful in designing algorithm? Okay. So, if I have to rephrase this, how can I rephrase this paragraph? Okay. So, let me rephrase this for you. Okay. Okay. So, what I am saying now, if you see an algorithm G comma K is a yes instance, okay, if and only if and only if this is an OR over, or this is AND OR over, right, OR over W in Sk plus 1 is a yes instance. Now do you see an algorithm? I did nothing, I just rephrased it, I just rewrote it. Right. So, what does this tells us? What does this, now this rephrasing of this lemma, what is it telling us? What algorithm does it tells us to write down? Basically I have wrote an algorithm, it is not that I have not written an algorithm, right. I can actually code this, it is a recursive algorithm, right. It is basically a recursive algorithm which does something. It says this is an AS instance if and only if now that we have proved this lemma, we know that one of them must lead to a solution if there is a solution, right. So, I am saying okay fine, then either this is a AS instance, like I do not know which one of them is a AS instance, but one of them actually is a AS instance, right. Either it is G minus V1, now I have decided to pick V1 into my solution, then in the remaining graph what size solution are you looking for? K minus 1. So, either this is a AS instance or maybe it is a V2 which is G minus V2 comma K minus 1. Okay. Now, you have seen NP, like NP. What does NP does? It finds a path in the, it guesses the path, right. Now, what I am trying to do? But how do I cannot guess this path, so I traverse every path. So, that is all. So, I look at the definition of NP, okay, and I just turn that into an algorithm, right. So, when you, but now we have to analyze, correctness is obvious, correctness of this algorithm is very obvious, right, because we have proved this lemma, which just tells that. So, basically now let us draw what is this tells us, okay. So, now I could also draw a tree, no, right. I could draw a tree which is says okay, here it is G comma K, right. Now, you are recursively calling how many instances? K plus 1 instances, okay. Okay. And here what I am saying, okay fine, it is G V minus 1. So, what decision I have made here? That V1 is the one which is in my solution, right. And then in the remaining graph I am looking for a vertex cover of size how much? K1 K minus 1, so on and right. So, this is what I have done actually. So, this lemma leads to this formulation leads to this tree, right. Right. Now, why did I say that this is exactly like, okay. So, what does NP machine tells you? NP machine is like, oh, at some point of time you make a guess. So, that is like making a guess. I say okay, try all possibility, and your guess is nothing but it says, oh, this is a yes, this is a correct yes instance if and only if there is a path from here to here to reach to the right place. Now, I have made a big tree where I am guaranteed that I at least capture a right path, that is it, right. So, whichever formulation looks easier to you, it is up to you to visualize, okay. But for me this is a right formulation, okay, that okay, I do not know which vertex will try, let me try out everybody, okay. I do not know which one, so I am saying okay, let me try to find a solution with this vertex. If I succeed, great. If not, if I failed in this path, then I come back, I said okay, let me try this path. If I succeed, great. If not, I will try. If I succeeded in either of them, then I have succeeded. But if I have failed in every one of them, then what is the meaning of that? It means I can deterministically say that it is a no instance because of the lemma, right. So, this is my algorithm, like nothing. So, if I have to write, what will I write? Vertex cover G comma K, right. This is my instance, okay. Okay. For all I in Sk plus 1, vertex cover G minus Vi K plus 1 I do, right, for I in, right. If for any like, okay, I need some base case, right. Right. What is a base case? I need some base case if I have to write algorithm, right. What is a base case here? So now I go, what will be my base case? So I say if k equal to 0, what should I check? K equal to 0 and G has an edge, return no, else return yes. So I wrote, there is nothing, there is absolutely nothing. You can go and code yourself in C program and this will work perfectly fine. If k equal to 0, we do this. If k is not equal to 0, I will come here and I will do these things. That is it. So this is my code. Okay. At least in C this will work. Do you have anyone has any issue with the algorithm? Right? What is the running time of this algorithm? That is not clear, okay, or that is also clear, but what should we do if we do not know the running time? Write down the recurrence. So let us write down the recurrence, but now recurrence has two parameters, n and k, okay. 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 So let us write down the recurrence. T on n vertices on k, okay. How many instances do I am going to call? So this is basically I don't know. Is that correct? Is this correct? So either this plus this running time of this instance plus this instance, but how many of them are there? K plus 1 of them there. So okay, this looks bit ugly, okay, we can make it nicer. How? I do not care about n, like I want to just say, okay, so this is definitely captures my running time appropriately exactly, okay. Now let me disengage n and k, right, because all I can say is like some n minus 1 k minus 1, but what is my one stopping condition? When k becomes 0, I do have a stopping condition, right. So I do not care at that stage what n is, right. So let me focus on that aspect. If I focus on that aspect, so let me ask, okay, I ask myself how many recursive calls, okay. So what I am saying, number of recursive calls is governed by what? Is governed by either decrease in n or decrease in k, right. I am going to focus on just k, okay. Now what it will be? So I am saying number of recursive calls, so let us call it L of k. How much, what is this L of k? Can I write this k plus 1 times L of k minus 1, right. Number of recursive calls I am going to have on instance of size k is upper bound, number of recursive call I am going to have on this instance plus this instance plus this instance. How many such instances? At most k plus 1 times this, right. What is this solves to? This you should be able to tell. Exactly. And this recurrence solves to, that is it, okay. But so basically that many recursive calls we are doing, and in each recursive call what are we doing, right? We are just finding some high degree vertices and we are deleting some vertex. So we are doing some polynomial amount of work at each recursive call. So what is the total running time? Total running time is number of recursive calls times amount time spent on each recursive call, right? Time spent on each, which is polynomial, right? Find, like what are you doing? You are sorting the vertices with high degree at each instance and then picking up top k plus 1, and when you are recursively calling someone else, you are just deleting this vertex and getting a reduced graph. All this work we can do in poly time. Okay? Okay. So, what running time of the algorithm we got? Okay. Okay. Let's look at other way of looking at it. Okay. Look other way of looking at it. Okay. This is obvious. Okay. Look at your tree. What is a factor of branching? How many leaves that you create at any point of time is k plus 1. What could be the depth of this tree? Right? What is the depth of this tree? Right? What is the depth of this tree? Look, in each bound k drops by 1. So, the depth is k. So, how many number of nodes, number of leaves is bounded by some k plus 1 to the power k, and since it is a branching, since every vertex has node 2, total number of leaves is like some twice of this. So, this also tells you picturesquely why this algorithm has only that many number of recursive calls, right. So, either you do your recurrence and feel good about it, or you draw a picture and feel good about it, right. In either cases you have to visualize how many recursive calls we make, and second thing, how much amount of time we spend on each recursive call, number of recursive calls, and how do I make it, right. Is that amount of time polynomial? Whatever, you have to multiply with that. Okay. Anybody has a question here? Or are we good? Anybody from the audience from far away? All good? Okay. Okay. So, let us take the message from here. Let us write down the lemma again, okay, and let us take the message from the lemma and let us try to massage the message. Okay. Okay. So, what I mean by this, so let me, okay, so I am going to leave this, and the heart of this was, what was the lemma we wrote? Okay. I am not going to write. Okay. So, our lemma was, if g comma k is a yes instance, then there exists a vertex covered S of size at most k such that S intersection is not equal to phi, right, and we did this algorithm. Okay. Excellent. Now, what was this? What was this? What was the, how many ways we try to find solution? How many?
K plus 1.
But that is the size of
Sk plus 1.
Sk plus 1. Okay. So, basically we should say other way, okay, Sk plus 1. So, now I am going to write Sk plus 1 to the power k algorithm. Okay. So, my algorithm is basically whatever that say it was. But what was the property of Sk plus 1? You said from here 1 must go into solution. Okay. What could be the natural strategy to improve this algorithm? What could, so I don't want with respect to vertex cover, but if you are thinking as a person, what do you go about it? Like what could you reduce, then you can say that, hey, then definitely my running time could improve. Exactly, right. So one natural strategy to reduce running time is come up with smaller s. Okay. Now what is the meaning of this smaller s? So let's try to refine this lemma. Okay. Like refine means, what I mean is like my wishful lemma. Let me write a wishful lemma. Okay. So this is my wish. So you understand, right? So like somehow, if for example, if the sk plus 1 was size say root k, what will be the running time this algorithm? Root k to the power k, right? So somehow there is something about it, right? But the main idea that is underpinning it is that what is the property of this sk plus 1 set? One must go, there exists a solution such that one must go into a okay.
I have a question. So, is it right to say that smaller sk plus 1 or s to improve the running time?
You are right, sk plus 1, s is anyway fixed. Okay. So so if I can say the following kind of lemma, right? If g comma k is a yes instance, okay, then okay, let's change it. Okay. Let W be a set computable in polynomial time such that if g comma k is a yes instance, okay, then there exists a vertex cover S of size at most k such that S intersection W is not equal to empty. This is my lemma, right, if I would like to prove. And in my current lemma, what is W? What is the role, which is the set W we are talking about, right? So here, so notice if I have such an object, then we will have an algorithm with running time W to the power k. If lemma is there, like lemma implies time algorithm, right? So running time depends on what? Size of W that we could come up with, okay. And in our previous algorithm, W was equal to what?
sk plus 1.
Right? W was equal to sk plus 1, right? So that automatically implied right. So there is nothing special about sk plus 1. All we are saying that if we can find some set W in polynomial time with the property that there exists an optimum solution such that it intersects with my given set, then I do have a branching algorithm or I do have a recursive algorithm that will find me a solution if exists one in time mod W to the power k. And just in the previous case, we could take W equal to Sk plus 1 and design such an algorithm, right. So, if my W was constant size, then what algorithm will we get? If W is of constant size, okay. So, what is this? This is basically, notice this is how you do things, okay. So, like you know something, you try to bring the ideas and put it on. So, this is basically an abstract reformulation, right. It just takes us out from this kind of Sk plus 1, like, oh, it is nothing special about Sk plus 1. It is, what is this? It is a set W which has a property that optimal intersects with this. So, the property on which our algorithm depended was on the fact that in poly time we could come up with a set such that my solution, my optimum solution intersected with this. So, basically this is the property. So, I have phrased this property into this lemma, that is it, right. So, now why it is useful? Because now we can forget about degree and this, we can think about finding W of, if we wanted to reduce the running time coming via this, all we have to do is find W as small as possible, okay. So, our new strategy is, what's our new strategy is? Our new strategy is find W as small as possible, okay. If W had size 23, what running time will we get?
23.
If, right, then we will get 23 to the power k time algorithm, right. Okay. Now, many of you of course know many of these things, okay. Can you come with a small W?
By the definition of vertex cover, every edge, one of the vertices must be there in
Yes.
the vertex cover.
So, what is W then?
If we pick an edge and pick two vertices as W.
Exactly, right. So, now what Sonic is saying is that, okay, if that is all that you care about, is that we know pick an edge, pick any edge E, say U equal to V, W equal to U comma B. We know any vertex cover, not even there exists any vertex cover of size at most k or not, that also does not matter. Any vertex cover must pick either U or V. So, now does anybody has doubt about this statement? Okay. Remember my lemma, okay. It has nothing to do with, for any problem, if you can prove such a lemma, you will have an algorithm, right. What I mean by this, such that if G comma k is a yes instance, I never even wrote a problem name, is a yes instance of some problem, I do not even know what problem, then there exists some solution, okay, let us not confuse ourselves. But all I am saying to you is that there is nothing about vertex cover here. If for any other problem you could prove such a lemma, then you could do the same algorithm, right. So, this is a generic lemma, this is a trick, okay. So, since this lemma can applied to any problem, let's give it a name, okay. What we'll give it a name? We'll give it a trick. We'll call it a trick. Okay, that's it. We don't have to give any name. It's okay. Anything which is slightly more general than a specific problem, let's call it a trick because it has farther reach. Okay. So does everybody now knows a 2 power k algorithm for vertex cover? Okay. So what do we know now? We know, okay. So basically what is this? Okay. G comma k is instance if and only if, let's write it down, no? If and only if G minus U comma k minus 1 some UB is in edge, okay, is yes instance or is yes instance. Right? All good? Okay. So now you will remember this trick. Okay. Okay. Okay, we will take a slight jump, or we'll change the track a little bit. So if anybody has any question on whatever we have learnt at this point of time, this is the right time to ask a question. Okay. I think we will come back. So up until now, what all algorithms we have seen for vertex cover? Let's try to understand what all algorithms we have seen for vertex cover. We first saw, so now in our arsenal, we had this trivial, let's see, let's write it here. So what is the first algorithm that we saw? We had this n choose k times n to the power big of 1 algorithm. This is the first algorithm we saw. Then we saw two randomized algorithms. Okay, two randomized algorithm. What were the two randomized algorithm? We saw one. Okay, what was this trick we applied? We call it randomly separated, right? So let's call them random separation. Okay, and what else did we found? What else did we do then? Then we had this 2.7 to the power k n to the power algorithm. What was that? Let's say colorful solution. Okay, so what was the true? What was the trick? Colorful solution. Okay, the first method, do random this, it's irrespective of problem. What happens after we made separated or we colored them is what will be a problem dependent. But the trick to randomly separate it or to color them, like every solution color them properly, is like it's a trick. So let's call them colorful solution. Or okay, so this is the two things we saw, and okay, and today we saw an algorithm running time k plus 1 to the power k n to the power big of 1 2 power k. Okay, okay, so let's so today we saw an algorithm with running time. Today we saw two deterministic algorithm. Okay, okay, but so what was that? First one was okay. What trick? What should be the give the name trick? let's call it small solution witness, okay? Small solution witness, right? Okay. So now I want to go back. The first algorithm that I made, okay? Okay. If you remember, I said, now notice we made one amazing algorithm in the first lecture when parameterized by n number of vertices. What was that algorithm? If do you remember? We said, hey, try n choose k, and this is at most this. Now you have also made this algorithm. Is this algorithm more powerful, this algorithm now? Think about it. What is an upper bound on k? K is upper bounded by n, right? So I could run this algorithm and that runs in 2 power n time, right? So now, okay, but this algorithm, if notice, if this algorithm k was like n by 2, say k equal to n by 2, what is the running time of this algorithm? Let's compare. Okay, so you understand my point? So definitely this, now let me show you why this algorithm is better than this algorithm for a minute. Okay. Okay. So what should I rub? Okay, now we can rub this. This we don't need. Okay. Please remember this abstract. Like if you remember this 10 such things, you don't need to remember anything from my course. That's all that you need to remember. Rest are just examples to instantiate. Okay. Okay. Now look at this. Okay. Look at this. Okay. So now look at this algorithm and suppose k is like n over 2. What is this algorithm running time? N choose n by 2 into the power big of 1. So what is this? This is like, this is exactly this. Number of subsets of size n by 2 is basically 2 power n divided by some polynomial in n. Okay, so nothing would change. But if I apply this algorithm, let's see, or I could apply this algorithm, which is, what is this algorithm? So we did much better. Okay, so let's ask ourselves slightly better question then, right? So this algorithm was somehow more sensitive to what solution you were looking for. Of course, if you are looking for something very equal to like n minus 1 or n minus 5, I mean, right, close to n, then the guy has no choice. Okay, but if this algorithm is going to take time. But now the next question is, then could we do better than 2 power n? Like look, even this algorithm, if k is like n, it's like 2 power n. So it's just that it is good, like it's already good when like the guy is very bad. You get my point, right? So like n by 2 itself, this algorithm is like, yeah, I'm very bad, but this algorithm is very good at that point of time. But now my question is, can we get an algorithm with running time 2 power n where like, or rather say 2 minus c to the power n, where c is some strictly less than, c is some fixed constant. Okay.
This is the power n, right?
Yeah. Where? It is n.
No. Below 1.4. That.
Yeah, of course. I am not making p equal to np. Mistake. Okay, right? So we started with this algorithm. Now my question is, now we detoured, we very hard work, and we made algorithm which, if I substitute k equal to n, it just meets my algorithm. Then say, can I use this algorithm smartly and do better than 2 power n, right? So, let us see what smartly will mean. Okay. So, I am going to just give you an idea and I will let you explore. Okay. Okay. So, this is an exploration question, okay, but I would request you to please go explore. Okay. Okay. Next time I will ask you the number. I will not ask you how you got it, but I will ask you number. Okay. Or if you do it yourself, please send me. Okay. So, what is an idea? Okay. So, I also told you a formula last time. Okay. What was the formula? What was the formula n choose alpha n? Tell me. 1 by alpha? No, it was just alpha, no? N. Right? This is the formula. Now, look at the range of k. Like suppose this is k. Okay. Now, look at your range around. So, this is like say k, say n over 2. Find a small range. What should you run here? What algorithm should you run here? This algorithm, right? What should you run here? I do not know what is this. Choose a small range around n by 2, maybe 0.45 n to 0.55 n. Okay? You run this 2 power k algorithm. You are doing great for these values of k. And now here, right? What should I be doing here? In the red zone, what should I do? If I just do even this algorithm, because of this formula, I should be doing better than 2 power n, right? Because number of sets. So, for example, if you do this, okay, just like you do the maths now, when you have someone, so calculator, look at this. This is like, what is n choose 0.45 n. I guarantee you this is less than 2 power n. Just do this computation here, no? So, and that is what will be here, because it only decrease, right? Because what is this? Because n choose alpha n is also equal to n choose n minus alpha n, right? So, if I find a opt maximum here, I have also taken care of everybody else. And in this range, if this is less than 2, then and this range, if what is 2.55 to the power n? It is definitely not 2 power n, because this number is not 1. So, this is also I am doing well. So, I am definitely doing well. So, what are your, okay, so what is your question? So, I have told you algorithm, only thing which I did not do is optimize. So, what is the question for you? Optimize. Okay. Optimize this idea and tell me a number. Okay. Right. So, you look, all I am trying to tell you, see why this algorithm will be good. See why this algorithm will be good, right? Because intuitively I know number of subsets here is very small, and here I will apply different algorithm which will do better than enumerating all subsets, right, and hence I will succeed. So, I do not care about here anyway, because number of subsets itself is less than 2 power n, so nothing. And where the hard part of this algorithm comes, I will apply some different algorithm and beat that algorithm, right. So, basically what happens, which means that this algorithm is not looking at every subset of size n by 2, it is a smart algorithm, right. Look at for k equal to n by 2, how many subsets we have? 2 power n, but this algorithm only takes time 1.414 to the power n, it cannot see more than 1.414 to the power n number of subsets. So, in the search space where there are n by n choose to, this algorithm is doing something very smart. So, this is a smart algorithm, right, because it is not looking at all n choose n by 2 subset, because they are 2 power n, and the running time of this algorithm itself is 1.414 to the power n, right, or 2 to the power n by 2 or root 2 to the power n. So, it cannot be looking at every subset of size n by 2. So, it is doing something smart. So, if what we did, we designed an algorithm which navigates through the solution space in a smart way. Okay. Is the analogy and idea clear, right? More and more you will do, you will start to feel these things. But like this 2 power k algorithm is not enumerating all subset. This is all that I wanted to tell you, right? So, it is really a smart algorithm than n choose n by 2, right? So, I told you doing some numbers computation that day, but I also wanted to feel it why designing these algorithms requires hard work, because you have to do a smart search of your solution space. Okay. Okay. So, this is an exercise which and like it does not have to be individual. You all can get together and give me the number using this strategy. I do not want you to come up with a new algorithm. No, strategy is very simple. Either you apply enumerate subset or you can apply this 2 power k algorithm. Okay. 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 And I will let these way of designing W solution witness for this lecture. I am not trying to make, we can make this 2 power k algorithm even better, but we will not do that now. We will get there in due course. Okay. We will go somewhere else now. Okay. So, where am I want to go? Okay. I want to go here. Okay. So, now I am going to focus back. I am going to focus back on what algorithm did we made? This algorithm. Okay. What was the property of W? What was the property of W? Okay. There was a right. The property of W was that there exists S such that S intersection W is not equal to phi. This was the property. I want even better W. I said I want to say that in fact I can find a W such that like all we guarantee that S intersection W is 1. What would be a strengthening of this lemma? Like what could be even more ideal situation?
It's more than 1.
More than 1. So, what will the idealistic situation for this? Look, we proved 1. She says the good would have been, maybe we can say, so her sense of good, what is a better statement or a strengthening of statement could be a strengthening of statement. What is a strengthening of statement? She says, oh, there exists S such that S intersection W is at least 2, right. So, if this is a strengthening, what could be further strengthening? 3. So, what is the most idealistic situation?
Or S equal to W.
No, S is contained inside W. If I knew some W, so this is my idealistic situation. Okay. So, what is my ideal world? Let us see. Okay. So, here is my ideal statement, and then we will see what does ideal statement would imply. Okay. So, what I want to say, I mean there could be, okay. Okay. So, I want to just take poly time for now. Okay. So, what is, there exists a polynomial time algorithm that computes a set W such that there exists a vertex cover S of size at most k such that there exists that is contained in W. This is my ideal statement.
I have a question. It may be a very stupid question. Like, is there any reason why taking W to be the first k plus 1 high degree vertices, would it not be suffice to take only k, and then we would have said that W equals to S?
There I could only prove one, that only one vertex is contained inside that. I couldn't prove two even. I am saying W is fully sitting inside this, right. If I draw a picture, here is my W and here is S. Now, like it is in the lap of W. Okay. Can you come up with any W? Forget about, I am not talking about anything useful. Can you think of any W? Great. Okay. Excellent. Okay. So, at least my statement is not like not that bad, right. I mean, there are like it is not that it is bad. Okay. So, you say take okay, fine. What algorithm will this give? This will exactly give you this algorithm, right. But if I could find a W, what kind of algorithm could we get? Look, if I prove this ideal statement, then what kind of algorithm will we get? Do we need to enumerate what? W choose k, k to the power big of 1, right. Do you agree? I mean, you told me that S is fully inside W, then why should I look for k size subset somewhere else? I should be looking for a k size subset which is fully contained inside W. Okay. So, at least this gives us this kind of algorithm. Okay. But W equal to Vg does not give us an algorithm, right, if we take W equal to Vg, this is as good as enumerating all right. Okay. So, at least the moment some statement is true, what are some basic questions to ask? This statement is true for W equal to Vg. Okay. Now, you ask yourself, what kind of W could give us an algorithm of running time, say if I ask you some suppose I wanted W choose k to be some, I want an FPT algorithm. Okay. So, let us say, okay, or rather let us say if I ask what should be size of W such that W choose k is upper bounded by some f of k. What should be the function? What should be the W? What is this? W should also be function of k. Agreed? W should also be function of k. Okay. Okay. So, ideal world, right? If we wanted to design an FPT algorithm, okay, if I wanted to design an FPT algorithm, what should I want? Desire. So, what is our desire? What is our desire? Desire is compute W such that cardinality of W is some f of k. Okay. There can be, okay. So, what can be two things? Either exists or does not exist, right? Maybe such W exists or such W does not exist. I mean, this approach may not work. I mean, in look, my algorithm has to compute something in polynomial time. Maybe this W exists, but they are not polytime computable, right? So, this W may exist or may not exist. I have no idea. If it exists, I know how to use it, but it may not exist. How to prove this, right? How to prove that just such a statement does not exist? Such a set, like I cannot prove such a statement, right? You look very confused on it, right? So, what I am saying to you that what you mean by or does not exist, okay? Ideal statement with cardinality of W being equal to f of k, okay, does not exist. This is what I mean, okay. Okay. But suppose it exists, what should be the algorithmic way of doing it? Okay, if it exists, how small W could be, right? So, you look at the several questions that comes into picture, right? Can I show first of all such W, whether such W exists or does not exist, okay? If it does not exist, let us forget it. If it exists, what is the smallest size W that we could hope for? Okay, if we found some size W, is there anything smaller, or I can prove that anything smaller than this is not possible. So, I am saying that you have all kind of natural questions coming out once you want to prove such a statement. Once you want to prove such a statement, a new research directions open. What is this? Does W exist? Okay. If W exists, what is the smallest size? Oh, I found some size. Can I do better, or is it all that we want? For example, look at running time of polynomial time algorithm. Oh, we got polytime. Is NQ the right number or n square? Can I go to n square? Oh, I got n square. Can I show that n to the power 2 minus epsilon is not possible, right? So, various questions start to emerge, starting with trying to prove a version of our ideal statement. Okay? You understand my point? Okay. Okay. So, how small W could be? Okay. Ideally, like the most ideal which we love is most desired, okay, is when W is size poly in K. That is something which we like, okay. I know lot of people will be relating it with something, but think for a moment, it is not what you think. Okay. So, what are we saying? Let me tell you what are we trying to say in picture. Here is my big graph. This is my G. All I am trying to tell you, can you come up with in poly time a set W which has size f of k or k to the power big of 1 such that there exists an optimum S sitting inside this, right? This is what we want. So, what should we call this technique if we able to achieve? What should we, right? Search space reducer, search space reducer or reduction, whatever. Let us call it search space reduction, okay. Let us call this, let us give it search space reduction. Okay. Okay. Right, search space reduction. So, let's try to do some search space reduction for vertex cover. That is what we want to do. Okay. So, can we do some search space reduction for vertex cover? Okay. So, is the overall methodology clear, right? So, we are just, what are we trying to do? So, there are like, these are like very natural steps to take. If I look at this n choose k, right, what will I think if I don't know anything? Oh, can I replace n with some function of k? Can I replace n with function of k? Then I know, because when I started up doing parameterized algorithm, all I knew is n choose k. So, I will write n choose k on this, and then suddenly you realize, what are we trying to, like after a few days of thinking, you will say, how could I do something that my running time of algorithm will be f of k? Forget about problem, right? What can I do? I first need that kind of strategy, So, we will say, oh, can I do something that I can replace n with some f of k, and then I am done, because that is all that algorithm I know, n choose k. Try, but maybe the moment you do this, you have made something interesting in your head. What are you trying to say? Oh, I don't want to look for all subsets, but I only want to look for some interesting subsets and find my answer. So, basically among the search space, you want to not navigate everywhere, but only navigate among small subsets, right. So, it is an idea, right. Implementation is a very different strategy, but I am only talking about idea, right. What is an idea? If we can reduce the search space to something more meaningful, and meaningful will change in the context. So, in our context, this is some set of objects whose size is bounded by function of k, where we want to do our brute force or exhaustive search. Okay. Okay. Let us try to prove this ideal statement with slightly greater than w equal to vj, okay, for vertex cover. Okay. Okay. Is the strategy, idea, goal clear to everybody? Okay. And to again, to all of them, this is not what you think. We will get there. Okay. Concepts did not come flying, they come linearly. So, I am trying to teach you the way the field has grown, or at least the way I view the field has grown. It is like, okay. Okay. So, let us say now what we want to do. So, we talked philosophy, let us do the implementation of philosophy. Okay. So, now we want to implement the strategy for vertex cover. Okay. Suppose I have a graph G here, and I have a vertex whose degree is 0. Is this useful for us? Anyhow? No, right? So, what should I do? Delete, right? But then when you delete, your answer might change. You have to make sure that when you delete, your answer does not change, right? Right? So, we have to prove something. What we have to prove? Suppose this vertex is V, okay? Then what we want to say? That answer does not change, right? You can do whatever you want to do, okay? So, he wants to do some reductions, right? After all, we are doing search space reduction. So, we want to do some reductions without changing answer, right? Right? Without changing answer. Otherwise, if you change the answer, then like it does not make sense. So, what should be the statement should be proving it? So, we should prove that G comma K is a yes instance if and only if G minus V comma K is a yes instance. So, whenever you apply a rule, what is your rule? What is your rule? What is the rule you wrote? So, here is your rule. Let us write on your rule. Let V be a degree 0 vertex. Let V be a degree 0 vertex, then delete V, right. So, this is a rule, and what does this lemma will give us? What will this lemma give us? Correctness of the rule. This is correctness of rule. So, whenever you apply your rule, you also need to prove that your rule is correct. And how do you prove rule is correct? So, whatever operation you are applying, it is justified and you prove this statement always. And of course, another thing is running time. It's poly time, right? I can find a vertex of degree 0 in polynomial time. And how many times can I apply this reduction rule? At most n times, because so in total applying this rule is just poly time. But is this statement correct? Does everybody believes me that G comma K is an S instant? So look at a vertex cover of size K. Definitely that's a vertex cover here because it's a smaller graph. In the backward direction, look at a vertex cover of size K. Look at this. That covers every edge because every edge in G is also present in G minus V because V has no edge incident. Look, I said verbose, but like please write it for yourself or convince yourself. Okay. Okay. What more rules? Lot of you people have seen lots of rules, but then leave it. Then don't tell. Let new people think about it. Okay? What other rules can we think of? What was the basis of our first algorithm? Of her algorithm. What was her basis?
So if one vertex exists, then we
What did the first algorithm did? Or the first deterministic algorithm? Huh? No. Today's deterministic algorithm, FPT1. It branched on Sk plus 1. Let's focus on V1. This is my P1, okay? It's maximum. It has some neighbors, right? When can we say there exists a solution S that contains V1? Huh? Huh? What? All the neighbors? No, I want you to tell me that, look, if this happens, then this must happen. Look, I told you, right, irrespective of what, if there's, look at the K plus 1 vertex, it must. Now I'm saying, can you come up with a sufficient condition? What I'm saying, can you come up with a sufficient condition on V1 to say, hey, look, what did we say? Look at the highest degree vertex. We know it is not part of an optimum solution. When can I say that highest degree vertex belongs to my optimum solution? This is what I'm saying. Like, it is not necessary that a highest degree vertex must belong to my solution, but maybe there are some situation where the highest vertex could belong to my optimum solution. Can we figure that out? You understand my point? Yes. Okay. So what is Ajay saying is that suppose degree of V1 is greater than K. What can you say? It has at least K neighbors. If you don't pick V1, what is going to happen then? Who is going to cover these edges? Remember your branching algorithm. What did you say? Either this vertex or that vertex must go into the solution. Now, from each edge you decided that this vertex does not go into the solution, then you have to pick each of them. What is the size of the solution?
greater than K.
Greater than K. Not possible, no? So, if you are looking for a solution of size at most K, you better pick V1, right? So, we automatically get, so like in general this statement is not true, but in some situation the heuristic that high degree vertex is useful, or we could form an optimum solution containing high degree vertex, is possible. So, this is called like necessary, like if this happens then this should happen. So, we found some local condition and say, hey, if this situation arises, we have an opportunity to apply rule, right? So what should be the rule here? So what is the rule? What's the rule? If degree of V is greater than K, then what is the rule? G minus V, comma K minus 1. So what should be the correctness lemma? Correctness lemma is G comma K is a yes instance if and only if G minus V comma K minus 1 is a yes instance. Is that good? Suppose I have a bucket whose capacity is that it can contain 10 mangoes. So if I have 5 buckets, how many mangoes can it contain? 50. That's great. So should I prove the correctness of this rule, or can you prove it yourself? Okay. So I am saying to you that now we have constructed our W. Think. And I just told you an argument. Think of every vertex as a bucket. How many mangoes can it contain? No. How many? At most K. So if you pick K of them, how many can it contain? Or how many can it cover? K square. Isn't it like a mangoes and buckets? Right? And that's it. Okay. So we applied degree 0 rule. We applied this high degree rule. Okay. I do not want to delete this. What should I delete? I do not want to even delete this. I am going to delete the correctness. I want to keep the rules. Okay. You understand how the correctness is proved. Okay. So let's try to understand what happened. Okay. Apply rule 1 and rule 2. Okay. Apply rule 1, that was degree 0 rule. Okay. This is rule 1. This is rule 2. It's 1048. Okay. Exhaustively. We also need some base case. Okay. What are some base cases? Can you tell me some base case? G comma 0 is your base case. Can I say something if I see G comma 0? If G is non-empty, say no instance. So, I mean, I can also, if I can solve the problem, then I solve the problem. I solve the problem, right? But look, I have never changed my answer. So it's okay if after applying some reduction rule, I have applied correctly and I am able to conclude to you that it's a no instance. Then I basically have solved the problem in poly time. Great. Or, so if G is non-empty, if G is non-empty, like if we are able to, if G is non-empty, say no instance, right? Okay. So we have some of these kind of basic rules. But what happened, right? Now, what should be another rule? Can I say this? If number of edges is greater than how much? K square, then what should I say? Return? Is this fine? Why? Because look at any K vertex. You are not able to apply any reduction rule, which implies what? Like maximum degree of this graph is upper bounded by K. So every vertex could cover how many edges? How many edges? So total number of possible edges covered, total number of edges k vertices could cover is at most k times k, which is k square. So, if I have more than k square edges, I am done. Okay. How many vertices are there in this graph? How many vertices are there? You will see how many vertices are there in this graph. There are only that many edges, I agreed, but how many vertices are there? Huh? He says 2k square.
K square plus k.
There are k square edges, right? So, how many? I think he's right. I mean, 2k square should count everything, no? Then where did I use degree 1 rule? Rule 1, where did I use it? This only counts, if you notice, edges, vertices with non-degree 0. Vertices with degree at least 1, because then only some edge is incident, no? It does not count degree 0 vertices. This argument, and that is why we needed this, that delete all degree 0 vertices, otherwise I can't bound VG. Right. So, VG is, everybody is right, is roughly 2k square. Maybe it is, okay. So, vertex set is upper bounded by 2 times k square, because that many edges count both endpoints. Fine. So, what is our W? So, suppose we had this G comma K, we applied this P time procedure and produced G prime, K prime. And what is the property of this procedure? What is the property of this procedure that we made? Right? That we never change the answer. Right? So, basically G comma K is a yes instance if and only if G prime, K prime is a yes instance. What is my W? What is my W now? Tell me, what's the W? What can I take W as? Huh? No, but what is the W?
The whole
Vertex set of?
this reduced G prime.
Yes. So, now I take W equal to vertex set of G prime, and what is the W? It's k square, 2k square. Okay? Okay. But this is strange, you know. So, it's a much, we proved something even more stronger actually. What we proved actually, what I mean by stronger is that this W is not contained inside. So, the kind of object we wanted to look was like W is like something which is contained inside, but W is actually equal to V of G prime. We were able to take this. So, this is kind of special. My statement does not demand that W has to be the whole instance size. W could be something much smaller inside, right? It's just that in this case, we were able to give you instance which whole itself was nice for me, so I didn't care. But maybe there could be problems for which I may not be able to bound every aspect of the input, but I say, hey, look into this smaller object, you have your solution. But this is very special because what happened? We were able to reduce the whole instance itself. Okay? Okay, we will give it a name at right time. Okay, we will not go here. So, now what is the natural question to think? Given this W, given this W, what are the natural question? What are the questions that you can think of? What could we try? Can we find smaller w? Or could we prove there is no, we can't find w with size order k2 minus epsilon. I mean, this is like because you already find k square. Okay, 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 fine. So we will deal with this world. We will prove, in some sense, we will prove both, but both. We will also find a smaller w, and we will also prove that we can't find w, which is this. But like, what will that mean? We will make it clear as we go forward. But we will prove both. Okay. Okay. You will see. Okay. So we wrote this. We did amazingly search space reduction. What did this algorithm gives us? Now, so what will this algorithm? This is very simple, right? I take g comma k, apply this polytime procedure. So what does this algorithm tells us? Look. So what is this? So what is my algorithm now? Okay. So algorithm is given gk, apply this p time procedure, okay, and do search space reduction. And here, now that we have done search post reduction, do exhaustive search, right? And this will be like 2k square, choose k, n to the power big O of 1, which is basically k to the power big O of k times n to the power big O of 1. Okay, that's it. So this is an algorithm. So we are just designing all kinds of algorithm. Okay. So just let's be. I still have 2-3 minutes. I want to take one more reduction though. Okay. What do you think about degree 1 reduction? Degree 1 vertex. Degree 0 you told I can remove. Can you say the same about degree 1? What can you say? Okay. So there could be a rule, right? So what you all are saying, let's make a rule, right? And what is an idea? Look at a degree 1 vertex. You know that one of these vertices will be in the solution. What is the point of picking V? Because V can only cover this edge, but if I pick W, it might be able to cover many more edges. Okay. So our rule will be if there exists a vertex V such that degree of V is 1, then G minus V k minus 1, and this is correct. What does this rule gives you? If I take trees, if I take this tree, apply rule on trees, what will we get? Keep doing this, you will solve the problem of vertex covered in polytime, right? Because you always are guaranteed to apply this reduction rule, right? So this gives you a polytime algorithm, apply rule on trees, gives you polynomial time algorithm, vertex covered on trees. Okay, so these rules are very interesting in itself, right? That for a large class of instances, if you just apply this rule, you are able to solve the problem in polytime, right? For example, just by applying this degree 1 rule, we are able to solve vertex cover in polynomial time on trees, right? So, any more questions? Okay, that's all that I wanted to say. And next class, we will further explore this direction. Yes?
So, in the flowchart, our actual goal is to find MPT. So, in the first step,
Yeah.
instead of P time, if we spend the MPT time,
We are not getting there. Of course, we can do all those things, but like we'll get there. My students, like, we'll get there. On purpose, it is written the way it is written. Those are the things which one can itself do it, right? So, like, it's an exploration. We'll get there.
I have a question.
Please ask.
So in the last
But but you can do it. That's all that I'm saying to you.
in the last rule, we are choosing the degree 1 vertex or we are not choosing?
Okay. I'm not finding a solution. I'm just doing decision version, right?
No, that I understand. So
Huh.
my rule is a degree.
Oh,
1
right. You're
vertex.
right. No, you're right.
No,
I,
10K.
Yeah,
That
right.
is my doubt actually. K
if there is a vertex V such that degree V equal to 1, then it should be n of V. Because you take its neighbors, right? So you delete that vertex because you have decided to pick that vertex in its neighborhood into.
You should delete the neighborhood of.
Okay, so I think all of you are right. Such that let W equal to n of V. Correct. This is fine.
No, it will be V only because we are deleting V and we are putting the neighbor in the solution.
So
A
that degree 0 rule will take care of itself. Huh? You apply this.
Are you removing the edge here now?
I am deleting W, where W is n of V. W is a neighborhood of V. V is a degree 1 vertex. Yeah. Here it is V and here is a W. I am deleting this W. If you look, it will create V as a degree 0 vertex, but degree 0 vertex we have a rule for degree 0 vertex. Look, I'm saying if I add this extra rule and apply all the rules from previously, you can solve vertex cover in polytime. Like, it's in fact just degree 0 and degree 1 rule are enough to solve vertex cover. Okay, so look, what choice we made? Which choice we made is that there exists an optimum vertex cover containing W, right? Why? Because if it contains V, replace V, add W, that's still a vertex cover. That's it. Okay, so if W is neighbor of V, then you delete W and decrease K minus 1 and apply rule. Which rules? Degree 0 plus degree 1 rule on trees, and that will give you polynomial time algorithm. Because if you delete W, this will become degree 0. So you just delete it. And we know how to do degree 0 reduction. So all I'm saying, if you apply these two reduction rules exhaustively, at least decision version you can say yes or no, right? Because at some point of time you will get G comma 0. You check, is there a edge or not an edge? If it has an edge, you say no. If it has no edge, it's an AS instance. That's it.
So, like, can we reduce further, like degree 2 vertex?
Yeah, we can, but unfortunately I don't have time. But the problem is NP complete on tree cubic graph. So there could be some complications there. But 2, we should be able to do it, and we will do it next time.
So in 3 we can't.
Many situations we can. Yes.
So in this rule, you also have to ensure that the neighborhood of the V is strictly within.
No, absolutely no. Why? Look at a solution. If it doesn't contain V, it contains W. So you made a correct choice. If it contains V, delete V, put W. Is it still a vertex cover? Right? Because V was covering whom? Just this edge. Now I put W, it does exactly the same role as V. It might be doing some more role. That's it.
And it also cannot contain both V and W.
It shouldn't contain both. At least optimum solution shouldn't contain both V and W.
So if we write it as G minus V comma K, will it be equivalent?
No,
No.
that's not it.
So are you meant to say that it will be at least as good as V?
Huh?
It will be as good as.
No. Yeah, it is as good as, but why think from that perspective? As good. I gave you a formal proof. If there exists a solution containing V, then there exists a solution containing W. That's as formal as it gets. Why let's make an informal statement? This is a formal statement. If there exists an optimum solution S containing V, then I can make a same size solution that doesn't contain V and contains W. What is that? Delete V, add W. Okay, size remains the same, right? And every edge which was covered before is covered now. That's it.
So in these rules, our aim is to like reduce k.
Instance size.
Your W G is reduced.
Look at the zero rule. I mean, if both increases, can both increase in poly time all the time? Impossible.
But that like
Look at the degree 0 rule. Did k decrease? So, but something decreased, no? Size decreased.
no, but that's the thing that she told like g minus v comma k.
That's
What?
here. No, here in this rule, I am telling instead of W, we are taking V and
No, we are not taking V, we are taking W into our solution. W is a neighbor of V.
Yes, yes, I understand. I am giving another rule that G minus V and K we are not decreasing, keeping K. So
That will not work.
that will
Because you forgot V, this edge incident to. Who will remember the fact that this edge is covered in the reduced instance? You found some other solution. This is like bogus rule. So try to prove correctness, no? Then you will see how the bogusness of your reduction rule is. All you claimed, look, first you are making a structure statement. All you are claiming, look, there is an optimum solution containing this guy. That's all the decision you could prove it. If that's all that you could prove it, your rule should reflect that, no? Okay. Okay, that's all that I wanted to say.